You can see that I will show you the response in the next slide. Here the first for difference is the bandwidth is very wide in common emitter amplifier, whereas the bandwidth is very narrow in your tuned circuit. You know the relation between Q, F naught and bandwidth. Quality factor equal to F naught by bandwidth. So the bandwidth is large, then the quality factor will be less. That is for your common emitter amplifier. In tuned circuit, since my bandwidth is very narrow, it is going to possess a very high quality factor. So what we are going to say about quality factor is it can effectively amplify signals at a particular frequency f0 without loss in power. Okay, so the L and C will transfer their energies effectively without loss in energy or power, because the Q factor is going to be very, very high for this tuned amplifier. And tuned amplifier is mostly used in communication equipment, especially in receivers. To get signal from particular station, we are going to use this tuned amplifier. I have told you in the class example of a FM station, right? So depending on what frequency you enter in your mobile phone, that circuit is tuned to that particular frequency, and you start listening to the content which is provided by that particular radio station. Okay, so that is a very, very simple and most extensively used application of tuned amplifiers. So basics of tuned amplifier is very simple. In the collector side, instead of having RC, I'm going to have this tuned circuit. So since I'm going to replace RC with a tuned circuit, the circuit becomes frequency selective. So it is going to amplify signals only at F0, and all frequencies above and below F0 will be completely, the amplification will fall down. Okay, and the bandwidth is going to be FH minus FL, and it is going to be very, very narrow bandwidth for this tuned amplifier. And now you can see how the response of tuned amplifier. So this is the ideal response. So ideally, where in a very short band of frequencies, the amplification should happen. So the band where the amplification should happen is called as pass band. Other than pass band, this side and this side, you are going to have stop band. The stop band is the band of frequencies which is rejected by your amplifier. And pass band is the band of frequencies where amplification takes place to the maximum extent possible. This is ideal case. Ideally, I want a response like this. Ideally, the amplifier should be having a uniform gain from omega L to omega H, or FL to FH. Center frequency is given by omega naught or F naught. But practically, you see, we have done tuned amplifier experiment also in laboratory, right? And as a part of ADC lab. So you get this response. But whereas for common emitter, you get this response. So when you compare these two response, the bandwidth is large, but here you see only one particular, there is a peak. But in common emitter amplifier, you don't have a peak. The peak is going to be extending for a band of frequencies, but here the peak is well defined at a particular frequency F0. And when you draw 3 dB line, you can see how FL and FH are very close to F0. So the bandwidth is also going to be very, very narrow. And you know phase angle, at the resonant frequency, the circuit works like a resistor. So the phase angle becomes 0 at omega naught. So as the frequency increases beyond omega naught, the phase angle will increase. As the frequency goes below omega naught, the phase angle will decrease. At omega naught, the phase angle is 0. Okay, so this is the ideal response. The phase will be a straight line, but here the phase follows a curve. And ideally, the response is required to be rectangular response, but here you have a Gaussian shaped response here, having a peak at a particular frequency F0. So that is the characteristics of your tuned amplifier. And obviously the resonant frequency, you know this formula, we are using this formula wherever L and C comes, right? The F0 equal to 1 by 2 pi root of LC, or if you want to say in terms of omega naught equal to 1 by root of LC. So omega naught is the angular frequency in radians per second, and F naught is your actual frequency in hertz. Any doubt in the basics of tuned circuit? Anybody is having doubt on how this circuit is going to work? In the graphs, whatever we have seen. Okay. So the response is maximum at a particular frequency. That frequency is called as resonant frequencies. So for the frequencies, when you increase the frequency up below the F0, there is a very sharp decrease in the response curve. The response falls very sharply. Okay, so that is the reason why we are going to have a very low bandwidth for this tuned circuit. Okay, so at f naught you have maximum gain. On either side of f naught, whether you are going to decrease or whether you are going to increase, the gain is going to fall off very sharply compared to conventional common emitter amplifier. So that these are the different points which you can understand when you compare a common emitter amplifier with the tuned circuit.